We have learned support and confidence, these two measures, are not sufficient to describe association rule. So the problem becomes, what are additional interesting measures good enough to describe their relationships? So that's the reason we want to examine a little more, like a lift and a chi-square, whether they are good enough to describe as additional interesting measures. So lift has been popularly used in statistics as well. We look at the same table. Okay? The same table, we can think B means playing basketball, C means eating cereal. So we have the exact same distribution. Then for this contingency table, we can use lift to compute it. The lift is defined as this. B and C are two item sets. For rule B implies C, that confidence, if it's divided by C's support, we get lift. Or we can say if BC, this rule's support divided by B's support times C's support. Okay. So for this lift, the general rule is if the lift is 1, then these two items are independent. If it's greater than 1, they are positively correlated. If it is less than 1, they are negatively correlated. For our example data set, we will calculate the lift of B and C, and B and not C. We derive 0.89 and 1.33. Okay. Then from this data sets and the rules, we can see B and C should be negatively correlated because the lift is less than 1. B and not C are positively correlated because the lift is greater than 1. This actually fixes our problem because we know B and C should be negatively correlated. B and not C should be positively correlated. So this looks very nice. Let's look at another measure popularly used in statistics as well, called chi-square. In chi-square, the definition, we need to calculate the expected value. Okay, how to calculate expected value? You can see this 400 is a real value, it's observed value. But expected value is just based on the distribution. For example, C and not C, the distribution is 700 over 250. This is 3 to 1. Among 600 students, the 3 to 1, you will get 450 versus 150. In that case, we probably can see we still can use the rules, like if chi-square is 0, they are independent. If greater than 0, they are correlated either positively or negatively. So we need additional tests to see whether they are positively or negatively correlated. Now for our example, we can easily calculate chi-square should be almost 76. So B and C should be correlated. Further, we can say they are negatively correlated because the expected value is 450. The observed value is only 400. It's less. So these themes can solve the problem as well. But the problem becomes whether lift and chi-square are good in all the cases. Let's examine some interesting case. In this case, you probably can see this not B, not C actually is quite big. There are 100,000. Okay. These actually call null transactions because the transaction contain neither B nor C. And if we just look at B and C relationship, we probably see B and C should be negatively correlated because it's not easy to get B and C together. B and not C is far bigger. C and not B is also far bigger. But if we use the lift, we compute the lift B and C, we'll get this 8.44, which is far bigger than 1. That shows B and C should be strongly positively correlated. This seems not right. Even we try to use this same contingency table, we add the expected value, we do the computation, we will find chi-square is bigger than 0. In the meantime, the observed value is far bigger than expected value. So we also should say B and C are strongly positively correlated. This seems to be wrong. What's the problem? Actually, there are too many neurotransactions that may make things distorted. We need to fix it.